Alrighty, welcome back, my friends. Um, hopefully you got the message from the first video. Hopefully you're watching these in order. Obviously, that would be ideal. Just want to put another reminder. I'll put it in every single one of these videos for this week. That Thursday is shaping up to perhaps be a little bit dicey in terms of a high impact atmospheric river for the Bay Area. So keep an eye on your announcements in terms of whether or not we will actually hold class in person. Because if it's not going to be safe for us, then of course I would rather stay home and teach from home. So just keep an eye on your announcements for that. Okay, so we finished up talking about monsoons, and now I want to touch into tropical cyclones. So tropical cyclones, honestly, are probably one of my absolute favorite forces of nature. They are incredibly destructive, which that's not my favorite part, but it's the fact that they are just so large and beautiful and just a really interesting organization of Mother Nature. And I just think that this is just the most fascinating thing ever. So with that, let's get into the nitty-gritty details. So tropical cyclones, they are defined as really intense centers of low pressure, and they tend to form over tropical or subtropical oceans and are characterized by really intense convective activity, which means intense thunderstorm activity. That's what convective is. If you go back to the mechanisms of heat transfer, right, that we talked about, convection was one of them. So this vertical movement of energy. And then strong cyclonic circulation. So if we recall from our atmospheric circulation lectures, that cyclonic circulation in the northern hemisphere is that counterclockwise motion. In order to be considered a tropical cyclone, winds must equal or exceed 74 miles per hour. There's no contrasting air masses or fronts. So that's one thing that can kind of distinguish tropical cyclones from, say, what we call mid-latitude cyclones. So the impacts from that we see here in the Pacific Northwest. So we usually have systems that have a cold front and a warm front, and when those two fronts love each other so much, they can combine, and we call that an included front. But that does not exist for tropical cyclones. It's generally just hot. The source of energy that tropical cyclones have, massive quantity of latent heat that is released during the formation of these thunderstorm towers, and warm ocean waters. So if we remember this term latent heat from back when we talked about water, right, and special properties of water, well, latent heat was one of them. It's a warming process, right? And I think I even mentioned that it's really important when we're looking for tropical cyclone activity and when we're observing these really massive storms. So when this happens, it literally, in the formation of the thunderstorms, it's making the atmosphere warmer, which is really quite fascinating to me. But another really big source of energy and a really big part here is these warm ocean waters. That is key to tropical cyclone development as well as sustainment. That's why we don't see tropical cyclones here, right? In California, we don't get tropical cyclones because our ocean is too freaking cold. Right? So anything that wants to try and make its way up here pretty much gets killed almost instantly. Rapid de-intensification is what we call it. And perhaps you've heard some of these terms before, like typhoons, hurricanes, and cyclones. They literally all mean the same thing. They're just located in a different ocean basin, meaning typhoons happen in the Western Pacific, so those have impacts on like the Philippines and Japan and Asia. Whereas hurricanes, that's what we call them here in the East Pacific and the Atlantic. And then they call them cyclones for anywhere in the South Pacific and the South Indian, or in the Indian Ocean, excuse me. But they're all the same thing. We just name them differently. It kind of helps us know like where we're talking about. So we wouldn't say, for example, we wouldn't call anything here, a typhoon. So if you hear the word typhoon, then you know it's probably impacting Asia. So we use a scale in order to characterize tropical cyclones, and we call that the Saffir-Simpson scale. So you don't have to memorize any of these values for any stretch of the imagination, but I just want to bring some things into your purview. That the scale goes from a tropical disturbance all the way up to a category 5, and anything category 3 and higher is considered a major tropical cyclone, meaning it will likely have some really intense damages. I mean, like, look at this. The wind speed of 111 to 129 miles per hour is pretty crazy, I think. And then we use a similar scale for the West Pacific as well. It's kind of like it's like the Saffir-Simpson equivalent, basically. So even here in the United States, and we're talking about typhoons over in the West Pac, we'll say it's like a category 5 equivalent, but they would then call it a super typhoon because they like adding those terms. So, and they are very, very strict on the wind speed for the category. A few times they've actually upped a category after surveying damage. That was Hurricane Michael that happened in the state of Florida. And it was initially a category 4, but then after seeing all the destruction, they put it up to a category 5. Or they recategorized it, basically, which is pretty crazy. Just to view where all of these things happen, this is looking at the historical tracks and intensity, with the lighter or the cooler colors indicating a lower intensity and the warmer colors indicating, a greater intensity. What I would suggest is that you pause the video and really examine this map. Like, what do you see? What sticks out to you? What patterns do you observe? So pause the video, take a moment, and hopefully you paused. But some things that really stick out to me are the most intense tropical cyclones happen in the Western Pacific. And this, by the way, it has not been updated since 2017. Any of the books that I use, or even trying to find like a map just like this, doesn't have anything updated. So we would actually see several more red stripes over here in the Atlantic because we have had some very strong storms here in the last, since 2017. But something else I want to point out is notice how there's not any activity at the equator. There's also really not any activity in the southeastern Pacific, and we've only had one tropical cyclone in the South Atlantic. Usually because there's just the ingredients, the right ingredients are not in the mix in those regions. Speaking of ingredients, just like any good recipe, we gotta have all the ingredients in order for tropical cyclone activity to occur. First is warm sea surface temperatures, meaning greater than 80 degrees Fahrenheit. So that's pretty freaking toasty. But we need that heat to go pretty far down the water column, basically meaning it can't just be a super thin layer. It has to be a pretty substantive amount of water that is nice and warm. The reasoning for that is because hurricanes, as you saw in the couple slides ago, the wind speeds are huge. They are enormous winds, which churns up water very, very efficiently. So if you are churning up really cold water from the deep ocean, then you're going to choke yourself out, and the hurricane won't sustain itself. Then we need weak vertical wind shear. That means that we want a little bit of tilt just to kind of get us all the way up, upright, and have like a nice structured eye, but we don't want so much that we just continue on like floating away, right? We want everything to be nice and stacked and upright. And if it's not, then basically what I say is it blows the top off, basically, which is really quite fascinating. We need to be off of the equator, typically between 5 to 20 degrees north or south, because we need Coriolis, right? If you need to review what Coriolis is, of course, you are more than welcome to. I highly recommend it, actually, because it is kind of a weird and funky concept. But we need that spin, right? So, and Coriolis approaches 0 the closer we get to the equator. So we need that spin if we want to be a massive spinning system. We also need abundant atmospheric water vapor at these low to mid levels, basically meaning that hurricanes don't like dry air. They want to be nice and moist, and so in order to do that, then we can't have any dry air coming into the mix, because that can really hinder the potential development and sustainment of the tropical disturbance. We also need some sort of triggering disturbance. Basically, we need some sort of storm to start. These things don't just pop up out of nowhere. They usually start from a little baby storm, and as long as all these other ingredients are at play, then it can continue to organize and become a larger tropical cyclone. So, kind of cool. But we need all of these in order for development and sustainment. Here are just some key words that maybe you've heard before when maybe you've heard about hurricanes on the news, because we've had lots that have impacted the United States in the past years. But some things I want to just mention. One is the eye. So the eye is generally the most calm part of the storm. It's the very center. It's where the lowest pressure would be, and also the calm part of it, which is really kind of wild. And then we have an eye wall. And what's really fascinating to me anyway is that with the eye versus the eye wall, you have the calmest part of the storm in the eye and the most intense part of the storm right next to it. And this is a donut-shaped wall of intense convective activity surrounding the center of the storm, so we have the strongest winds and strongest rain. Just a kind of a sidebar there, we don't say that a storm makes landfall until the eye wall crosses a border there. Excuse me. So it's very distinct on that as well. Like, we've had hurricanes that have followed the East Coast but have never actually made landfall because the wall itself did not cross over land, which is really kind of wild. The last little key word here is rain bands. So just because the center of the storm doesn't hit doesn't mean that there aren't implications of weather and such outside of that center of the storm. So these are curved bands of thunderstorm-producing cumulonimbus clouds that surround the eye wall area. So that's what, it almost looks like cauliflower, but that's what this image here is trying to show. So the last thing I want to talk about in terms, for this video anyway, is just to look at some of these features again. So what's really fascinating is with the eye, and maybe you've seen it cleared out before, that clears out because there's air coming from the top and sinking down into the center. And as that air is sinking, it's warming and compressing and drying out. And so oftentimes, especially with really, really strong tropical cyclones, we see a very cleared out eye. And the eyes themselves can be anywhere from 10 to 20 to 30 miles across. We've seen some really large eyes out there. We've also seen some what we call pinhole eyes. So that will just kind of make way for potential intensity. Which is really quite fascinating as well. So in the next video, we'll talk about some of the destructive features of tropical cyclones. So I encourage you to kind of think about what you think would be the most destructive part. And then I'll kind of poke on some notable storms that have happened in the past. Okay, thank you as usual so much for watching. I appreciate your time and attention.